Okay, so welcome to this next video in which we are discussing the structure of the GluCl.channel. Right, so we just discussed this hydrophobic girdle or patch that you have at the 9' amino acid on these 5 membrane-spanning alpha helices. And we discussed how this is going to basically produce this blockage of the pore of the channel. Now, effectively, in GluCl channels, but not in the human cis-loop receptors, what you have is 2 more of these blockages, basically, and you're going to have another one at the -2 portion down here, so at -2', and another one at 2'. So you're going to have 2 more of these. So you're going to have one here effectively at 2', which I'll denote in orange, like so, where all 5 membrane-spanning alpha helices put in a certain amino acid residue, which is going to be a threonine residue, which I'll discuss in a moment. And at the -2' portion, you also have another one, where all of the amino acids are going to provide this ring of 5 amino acids that will close the pore. And these amino acids are all proteins. So let's now discuss the structure of threonine and proline. And by the way, I'll just give you the numbering of these amino acids if we use the more conventional way of labeling the amino acids. So if you take one of these protein subunits out, one of these, and actually count the amino acids from the start and label them in the normal way, what's the labeling of these amino acids here? Because it's not the 9', the 2', and the -2'. Instead, the labeling of this leucine at 9' is in fact leucine 254. So that's its actual position on the polypeptide. So if you count from the amino terminus and you count up to the 254th amino acid, then that's this 9' amino acid on the M2 alpha helix. Now, what then is 2'? Well, we can work it out because we know it's 7 amino acids less than this one here. So take 7 away from 254 and you'll get 247. So this is threonine 247 because I told you it was going to be a threonine here. Okay, and then finally at -2, that's 4 less than 2'. Okay, so what we then need to do is subtract off another 4 from this, and we'll get that this proline is at position 243. Right, so now let me show you the structure of these 2 amino acids, threonine and proline. Okay, so we'll start with threonine. So threonine, here's the amino terminus here. Okay, here's the alpha carbon with a hydrogen coming off the alpha carbon. And then the R group of threonine is that you have a methylene group, like so. You then have a carbon coming off like so. Oh, sorry, you have an alcohol group coming off here, and you also have a methyl group coming off here. Right, so that's the structure of threonine. And you can see that threonine isn't as hydrophobic as leucine. Okay, so this isn't going to be as good a barrier to ions as leucine. Nevertheless, it does form a physical barrier in the pore of the channel. Okay, so you can see it's got this alcohol group, which is a polar group. Okay, so that's the structure of threonine. So you have these 5 threonine amino acids surrounding the pore at this 2' position, or 247 if you're using the more conventional way of naming the amino acids within a protein. Okay, now let's have a look at the structure of proline. So proline is a little bit more of an interesting amino acid. It's got a cycle in which involves this nitrogen here. So the nitrogen this time is not going to have a hydrogen on it, because instead it's going to be involved in a cycle which comes off the alpha carbon here and joins onto that amino group. There is still a hydrogen off the alpha carbon, and here's the carboxyl group as usual. But now there is this 5-membered ring basically between the nitrogen and the carbon here. And then off each of these carbons there will then be a hydrogen like so. Okay? And this is the structure of the amino acid proline. Okay, and the 3-letter amino acid code for proline is just pro, and the single-letter amino acid code for proline is just a P. Right, so that's the structure of the amino acid proline within a protein. So again, this ring is going to stick into the pore, and it will form a physical and also a hydrophobic barrier, because again, there's very little uneven distribution of charge here, so everything's going to be neutral against the movement of ions through. So that's the transmembrane region of these GluCl channels now, and we've discussed these gates which are stopping the movement of chloride anions through these GluCl channels prior to the ligand binding to the extracellular domain of the GluCl channel. Okay, so now let's move our attention to the intracellular domain first. So the easier one to discuss is the intracellular domain, and we might as well leave the extracellular domain until last when we come to actually discuss ligand binding there. So, the intracellular domain. So, just to remind you, remember that the structure of one of the subunits that makes up the GluCl channel looks something like this. So you have the extracellular domain with the cis loop here, and here's the amino terminus of the protein. Then you have these two, well, these are the first two membrane spanning alpha helices, then the next two, and in between these next two, the M3 and the M4 membrane spanning alpha helices, you have this large intracellular loop here, which is known as the M3 M4 loop, or also the intracellular loop. Now, basically, what you're going to have is you're going to have this hanging down from the bottom of each of the 5 subunits that make up the GluCl channel. So here is the GluCl channel here. So this is sitting in the phospholipid bilayer of the cell. So here's the phospholipid bilayer, and here's the pore of the GluCl channel, and then it's made up of these 5 subunits. So 1, 2, 3, 4, 5. Okay, and each one of these subunits has this M3, M4 intracellular loop hanging down like this. Now, it doesn't just hang down, basically. What happens is these M3, M4 loops that come off each one of these GluCl receptor subunits, they all come together at the bottom, basically, like so, and form this hanging basket-like structure. So let me show this as if we're looking from below. So basically, if we were to look from below, what we'd find is here's one M3, M4 loop, here's another M3, M4 loop, here's another one, then there are these other ones here, okay, and then they're hanging down from the bottom of the receptor. So here's the bottom of this GluCl channel here. Okay, and you can see that all of them are sort of converging to form this joint portion at the bottom. So they all come together and form this like basket structure with these holes in between the walls of the basket, which are made up of these M3, M4 loops. Okay, so in turquoise here, this is the M3, M4 loop. Here's one of them. And they all come together as they hang down from the bottom of these receptors and form this sort of net that's holding, that could hold things in principle. Right, now you also have these holes in between the M3, M4 loops which are next to each other, these holes here, and these holes are known as portals. Okay, so this is a portal. Right, now what is the function of this bottom portion of the GluCl channel? And by the way, this portion is known as the intracellular domain. So this hanging basket structure at the bottom of the GluCl channel is known as the intracellular domain and would be abbreviated to the ICD. So this is the ICD. Right, so basically the function of this intracellular domain is so that when ions move through the channel, so for instance when chloride anions move through the channel, okay, they're going to come in and their trajectory would be perpendicular or transverse to the membrane. So what do I mean by that? Basically, as they move through the channel, that's going to be the direction of their movement. In fact, I should draw this rather than using my pen. So the direction of their movement is going to be like that. Now, if they were to continue on this trajectory into the cell, what would happen? They'd end up right down here. They'd shoot off into the cytoplasm of the cell. Now, what was the point of bringing these chloride anions into the cell? Well, the point of bringing them in was to change the electrical potential difference across the membrane by bringing these negatively charged ions in, which will lower the electrical potential of the intracellular compartment. And since you're moving them out of the extracellular compartment, that will raise the electrical potential of the extracellular compartment. However, if you shoot them off into the cytoplasm, are they going to have much effect on the electrical potential of this area just below the membrane? The answer is no. And it's the electrical potential of the area just below the membrane that the proteins in the membrane are going to feel, the proteins which respond to electrical potential difference changes across the membrane. They're all in the membrane, so they are feeling the electrical potential on either side of the membrane, nearby the membrane. So it's no good changing the electrical potential in the deep cytoplasm of the cell. You need to change the electrical potential of the region near these proteins. So you need your chloride anions to stay near the membrane, basically. So you don't want them to have a trajectory whereby they shoot off into the cytoplasm of the cell. And that's the function of this intracellular domain. These chloride anions will zoom in here, they'll hit the bottom of this intracellular domain, and then they'll go zooming out one of the portals, basically. So they're deflected, and their trajectory now is going to be parallel to the plane of the cell membrane. So they're going to remain basically close to the inner leaflet of the phospholipid bilayer rather than going shooting off into the cytoplasm of the cell. And this means that they can better perform their function, which is, after all, to modify the electrical potential difference across the membrane. Right, so that's the function of the intracellular domain. Okay, we'll call it here for this video, and in the next video what we'll turn our attention to is the extracellular domain and ligand binding to this channel.